Hi, I'm James Onipede.
I'm Donwin.
And I'm Daniel Bunn.
What we're doing for what we did for our project is that we're optimizing the basketball pole. Right now in the basketball, right now many basketball park. The problem right now is that many park basketball goals tend to rock when they're dunked on or when the ball hits the rim. The rocking motion usually takes a while to stop, causing a delay in games. The customer needs is The customers are looking for a more sturdier pole that can reduce the rocking motion generated by outside forces, but also they want to reduce the volume to save money. The function of the pole is to support forces placed on the basketball goal in both the horizontal and the vertical direction.
Okay, so for our geometry and the material of the basketball pole, we used a standard 10-foot rim supplied from schooloutfitters.com. So the pole would be 10 foot above ground, while it is also 3 foot buried below ground, as well as the extension from the pole to the backboard is also 3 foot as well, while the diameter is 3.5 inches. So for the material, we used the ASTM A591 zinc coated steel with a modulus of elasticity of 29,000 KSI and a Poisson ratio of 0.29. So for the boundary conditions and the load, when creating our CAD, we made the pole 13 foot tall with a 3 foot extension to the backboard, as stated previously. For our boundary conditions, we encasted the bottom 3 foot of the pole to simulate the burial conditions in real life, as well as we applied a 200-pound load at the end where the rim would usually be, as well as apply the Young's modulus and the Poisson ratio as stated before.
So we are trying to minimize the volume while keeping the maximum deflection to less than 1/8 of an inch. We'll be doing this by optimizing the diameter of the pole, with that being one of the variables and the other variable being the load. The diameter of the pole must be between 1 and 6 inches, and the load being applied is between 200 and 300 pounds.
So for our design variables, we have two design variables, the diameter of the pole, which would be our X1, and the load on the pole, or the dunk load on the pole, which would be our X2. For our mathematical optimization statement, we will be using the first order Taylor series approximation, where the general equation can be seen on the slide right now. As stated before, we will be minimizing the volume while we are subject to the constraints of in diameter, load, and deflection.
So on the initial test, we chose a diameter of 3.5 inches and a load of 200 pounds. On the second test, we did a 5% increase on the diameter of the pole and then kept the load the same. And then on the final test, we went back to the original diameter for the pole and then did the 5% increase on the load. So now we're at 210 pounds.
So for the gradients that we were looking at was like for the change of diameter in regards to the function, you can see the numbers there, and also for the change in load in regards to the function, you can see the numbers there. And at the bottom, we see that with the change in diameter, you had the deflection was the function was essentially the Taylor series was essentially affected by that. But when we go to the bottom in regards to the load, that had no correlation whatsoever. So we had 0 for that. And for the arbitrary test, we used 4-inch diameter and a 230-pound load at the tip of the pole. giving us the deflection and the volume down there.
Right. So the arbitrary test was to test the accuracy of the Taylor series approximation. And as you can see from the Excel numbers on the screen, we had a 4.35% error for the maximum deflection and a 1.02% error for the volume. So these error values are pretty low. So that means our Taylor series approximation is pretty accurate, and we are able to go forward and find the optimal values for our basketball pole.
So for the MATLAB for the MATLAB optimization, the initial test values were 3.5 to 230, and we made our lower bounds from 1-inch increments to 200, through 200 pounds to 6 inches and 300 pounds. And you can see the results we got at the bottom with the thickness, the load, the deflection, and the volume. And also you can see here for the optimization test, the thickness from the previous slide resulted in 4.0763 as a thickness and a 200 load.
So for the predictions, we had a 1.4% error on the volume between the FEM value and the linear approximation. And then on the 23% error, or we had a 23% error in the deflection analysis between the FEM values and the linear approximation. The abacus analysis, it's a generally simple geometry, and then the point load, it should be accurate considering the real world situation. With the MATLAB analysis, we use the linear Taylor series approximation with the values taken from abacus. We do believe that a quadratic Taylor series approximation would be more accurate in this situation.
Right, and another reason why the error for the deflection could be so big is that the numbers that we're working with for the deflection are relatively small. So every change in the values could dramatically increase the percent error. But if we look at the differences in the FEM value and the linear approximation, you can see that the difference in them is relatively small, where the FEM value is 0.162 and the linear approximation is 0.125. So these are pretty good numbers for what we got. Finally, for our summary, for our project, we basically we try to optimize the volume of a basketball pole for a solid basketball pole that is also circular as well. But in the real world, there are many different types of basketball poles. And to improve on our project, we could test the different design parameters for these basketball poles, such as a hollow pole. We could change the shape of the pole or even the material, and the list goes on.
So by increasing the diameter of the solid pole by 1 inch, we can greatly increase the stiffness of the basketball pole. This can improve the quality of basketball on street courts by reducing wear on the hoops and the vibration of the poles while games are being played. In the era of COVID, park basketball has been the last resort for most players, which means there will be a high demand for stereo goals in the future. This would be a great solution into the future.